Yeah, so my name is Jarlath. Presentation is up here, machine learning AI for biosignal processing and medical applications. So I'm hoping this presentation is just going to give you a quick introduction to this here space, possibly even pique people's interest. So I thought it'd be good to maybe give an intro about who am I, sort of what qualifies me to actually be able to talk to you. So to give a bit of background on my education, so I have an MNG computer science degree from Queen's University Belfast, and I'm currently doing my computer science PhD at Queen's. And the PhD is looking at using AI for smart sensors and smart wearable devices and how we can reduce bias in these devices. So the research is hopefully going to focus towards the medical device scene and sort of how we can create new medical devices but make sure that they work for a wide demographic of people and there's no inherent bias injuries. So in terms of my experience with biosignal processing and analysis, I did work in retinal modeling where I tried to identify emergent network behavior across retinal ganglion cells. It's a bit of a mouthful. I also did EMG analysis, so working on optimizing that pipeline from data acquisition to AI model inference, as well as using the neural engineering framework for EMG classification. So that's what we're trying to use more biologically inspired neural networks to classify these signals. And then a bit of self-promotion here. I'm also the founder and CEO of Axonnr, it's an AI robotics company in Armagh, but there's a whole section dedicated to that later. Okay, so let's get stuck in. So biosignals, so I'm hoping this section is going to sort of let you know what are they, what they look like, and how we use them. So biosignals, so they're signals that can come from different areas to our body, including through our muscles, brain, heart, and they can be captured through both invasive and non-invasive methods. So for example, needle electrodes, which can be actually inserted into your muscles to capture EMG, or through non-invasive methods where we can just place a sensor on your skin and capture the signals that way. However, to give an actual definition or a term, biosignals can refer to both the electrical and non-electrical signals which are stored in the body. So common signals used in academia and research include EEG, ECG and EMG. We're going to look at those in more detail in the next slide. However, the important takeaway from this though is that biosignals are just like any other type of data we may capture in the wild. We can capture them, process them, analyze them, and find useful trends and patterns. Okay, so now we know what they actually are, but what do they look like? So we can see here in the slide we have three different types of biosignals. So we have EMG, which is electromyography, and that is the electrical signals produced when our muscles contract, and it's really good at being able to measure muscle activity. And then EEG is the electrical signals produced by our brain. And then lastly, we have ECG, electrocardiography, which is the electrical signals produced each time your heart beats. So now we know what they are, we know what they look like, I can use them. So for EMG, some of the big applications, we have robotic prosthetics, where we're trying to replace the functionality lost through a missing limb. We also have orthotic solutions, where we're trying to restore partial functionality from an intact but functionally impaired limb. And then a more interesting application is going to be rehabilitation through the likes of video games, VR, where we're trying to make that rehabilitation journey more engaging for our patient and really try to help them progress through that journey. Now, in terms of EEG applications, we have sort of this key buzzword, BCI, which is brain-computer interface, and this can allow an individual to open a communication channel with the machine and allow them to interact with their environment. So quite a popular application of this is a BCI controlled wheelchair, and that's something you see in research as well as on the internet as like the sort of the golden application of BCI. But other applications include seizure detection, where we can employ pattern recognition strategies to detect abnormal EEG signals, which will be characteristic of epileptic seizures, as well as assistive robotics, where we use EEG signals to create a communication system between the human brain and an output device. Lastly, for ECG, we can also do cardiovascular screening or disease classification, as well as cardiac abnormality detection, so detecting things like arrhythmia. And lastly, which is more popular, is ECG being used in the sports fitness training arena. So I know there's a company in Newry, and they're doing quite interesting work. I think they're actually working with the Premier League And the idea is that we can be using these biosignals to better understand how players are performing, say, during their training sessions or during their matches, and then use this information in a very data-driven way to improve. Okay, so that's that bit of theory out of the way. I also just wanted to cover a bit of theory around AI and machine learning because I can appreciate maybe not everybody has been exposed to it, so bear with me. Okay, so usually when we talk about artificial intelligence, there's three big buzzwords that come out. You have artificial intelligence, machine learning, and deep learning. So to sort of set the record straight, give a clear definition, artificial intelligence is, you can think it's like the umbrella term. It's the idea where a computer system can have some sort of resemblance to human intelligence. And then within that, we have machine learning, the subset. And machine learning is the ability of a computer system to learn based on samples of data. And then deep learning is this really interesting subset, which is more of a complex evolution of machine learning, where we're looking at things like neural nets, and these are networks that are trying to be more sort of inspired by the biological brain. So with that in mind, there's many machine learning algorithms available to us, but I'm just only going to cover some of the more popular ones. So for example, we have here KNN. It can identify clusters of similar data, objects, and users, and can be used for both classification and regression tasks. Now, quite a popular application of KNN is if you're looking to build some sort of recommendation tool. So we're looking to, say, recommend books, products, or movies. And that's why I have the likes of Netflix and YouTube, because when you think you're on Netflix or YouTube, you're watching something, they can recommend you something based on that watching history. Now, moving on to SVM. It's quite another popular machine learning algorithm, and SVM attempts to identify a plane that best separates a number of different classes. And it's primarily used for classification tasks. And quite an interesting application of SVM is in medical setting. It was used for breast cancer classification and detection, as well as gene classification. So it sort of ties in with the whole medical applications thing. And then lastly, random forest. Random forest is just made up of an ensemble of decision trees, and they help aid in the overall prediction of the algorithm. And applications in that you can find in the financial sector with regards to loan approvals, fraud detection, or stock market forecasting. And we're sort of now progressing from machine learning onto deep learning. You can see up here I have an example of a neural network. Now, it looks scary, but all a neural network is, you have an input layer where your data is fed into. You have X number of hidden layers, and then you have an output layer, which is where we get our prediction. Now, this particular type of neural net is called an MLP, or multi-layer perceptron. And you can see here, each layer of neurons is fully connected to the subsequent layer, where these arrows in the diagram, they will have a numeric weight attached to them. Now, sometimes when you're reading literature around this here, or even on blogs, you hear the idea of training a neural net. And all that means is you're providing the network with an input that you know the label for, and you're feeding that input forward through the network to get a prediction. And once you have that prediction, you're comparing it against your label and trying to determine how long was your network. And this gives us this error value. And it's at this point of the slide where this is where the fun maths takes place. But bear with me, I'll hopefully try to make it a bit more variable. So with our error value calculated, we use an optimization algorithm called gradient descent and a technique called backpropagation. And we try to calculate the gradients and try to reduce the error of our network. And the idea is that the more and more we do this, when we provide an input to the network plane, it should, in theory, be getting an output or prediction that is more closer to the correct label. That's in theory, sometimes it doesn't work. There's certain strategies you have to apply, but that's a whole other NIDEF kind of talk. Okay, so NLPs are great, but sometimes we need something more specialized for certain tasks. So for example, convolutional neural networks, or CNNs, are excellent neural nets for processing image data, because they're capable of reducing an image into only its essential features, and allows the data to understand and classify an image. That's why CNNs are sort of the foundation of most computer vision technologies. So moving on to this LSTM, or long short-term memory network, it's a type of recurrent neural network. that can process different kinds of information for arbitrarily long periods of time. And LSTMs are an excellent architecture when we're looking to model data that has some form of time aspect to it. So that's why LSTMs are very helpful for natural language processing tasks. For example, if you're looking to do speech recognition or if you're looking to do language translation. So that's all the theory out of it, if you do that now. We're on to the fun stuff. So this section is going over biosignal applications. So this particular application is going to use ECG signals. That's the signal we talked about. It comes from our heart. And within 30 seconds, you can record and save an ECG recording, and you'll receive results about your heart rate. So whether you have a high heart rate, a low heart rate, or even if you have signs of atrial fibrillation. And all of this here is done within a wearable form factor. So I've included the Apple Watch as a prime example of where biosignal analysis is being used in this wearable space. And the next application is a very famous and modern day example of where BCI is being utilised. So it showcases the ability to record neuronal activity through a chip implanted in the brain, and the ability of being able to perform real-time acquisition and processing of neural spectrum data and translating this data to some form of treatment or control interface. Okay, so progressing now from biosignal applications to medical applications. So epileptic seizure detection using EEG signals. So I'm not sure if anyone has epilepsy, but if you ever talk to people who are really into this here with regards to researchers or neurologists, an expert can detect epileptic activity by identifying specific patterns present in multi-channel EEG data. So what does that mean? So that means if we can implement a system that could non-invasively automate that pattern detection process, that'd be amazing. Because the output of that would be so useful, because we could then perform treatment before a seizure takes place through medicine, and it also serve as a really useful tool for researchers to better understand the effects of epilepsy. Now, our next medical application is going to focus on the idea of retinal prosthesis. So, basically, you imagine a device or a chip that we can implant into somebody who has blindness to restore their full sight or even part of their sight. Or we could even nearly bypass the degraded or damaged cells and replicate that functionality through neural prosthesis. This prosthesis could process the incoming visual stimuli from our world, encode that stimuli, send it onto the brain, and restore that neural pathway that was once broken through damaged cells. Now, all of this sounds like science fiction, but seem to break down the problem. It is very much doable. Difficult, but doable. And now the final application, robotic prosthetics. Now, I should give a wee spoiler. This topic I can talk in length about, and you'll see in the next slide why. But to give a quick overview, the ability to be able to interpret an individual's muscle signals is a very powerful thing. So when we perform a mobility movement, our muscles contract and produce a very specific pattern. So for example, the EMG produced when I make a fist is very different from the EMG produced when I give a thumbs up, and we can be able to distinguish between them. So building on this idea, this core foundation of being able to recognize different types of EMG patterns will allow us to restore the mobility for amputees, whether through upper limb or lower limb. And with that in mind, I'm going to introduce you to Axonnr. So Axonnr, we're an AI robotics company based in the lovely county of Armagh. We're looking to combine the latest developments of AI and robotics to revolutionise robotic prosthetics. So we're continually working on bringing the latest developments in technology to help clinicians and patients, and basically just give them access to the latest developments, so they don't need to be waiting 10 years to have access to these developments. Why not give it to them now? So our core technology is our brain-inspired control framework, which is delivered through our control system. Now, the plug-and-play ability of our control system allows clinicians to be able to operate their devices leveraging our technology. And the idea is to allow clinicians and patients to continually get access to and benefit from the latest advancements, ensuring that they aren't hindered by the underlying technology that comes shipped with their prosthetic device. So the idea is, as the advancements and developments continue, they can get access to them. And we're hoping this will potentially increase device uptake, because currently with amputees there's a very reduced device uptake, because say if it doesn't work, they get fed up because these devices cost an absolute fortune and they can't get a new one with all the features they're looking. So we're hoping this will address that problem. And then a good possibility of this technology is we can expand into other forms of prosthetic technology, such as lower limb, as well as other rehabilitative mobility devices. So I didn't have enough time to do a demo, but I was going to do a demo. However, if you keep an eye on our social media, I am planning on doing a YouTube series which is going to go in more in depth about biosignal processing and actually show you some code to be able to start your own projects if you want to get involved. And if anyone just wants to hear more information about Axonnr, or even just this topic in general, by all means, send me an email and I'll be happy to discuss it with you. And on that note, thank you very much.